Somewhere, far beyond the reach of even our most ambitious spacecraft, there exists a cosmic giant so massive, so staggeringly immense, that it makes our own sun, a blazing titan in our sky, look like nothing more than a glowing ember beside a roaring bonfire. This is UY Scuti, the largest star we have ever discovered, and if you think you know what big means, prepare to have your mind recalibrated. But before we continue, subscribe to the channel and like the video. We live in a universe where scale plays tricks on our comprehension. We can picture mountains, oceans, planets, but when it comes to the dimensions of stars, our imagination tends to break down. That's where UY Scuti comes in, a celestial heavyweight champion that challenges our very sense of proportion. Its sheer size isn't just a number in a textbook, it's an awe-inspiring fact that stretches the boundaries of what we thought possible in nature. Imagine standing on a distant planet orbiting this star, if such a place could exist, and looking up. The star wouldn't be a pinprick of light like we see in our night sky. It would dominate the heavens in a way that defies description, an endless horizon of fiery red stretching from one side of the sky to the other. This is no ordinary sun. This is a swollen, bloated, aging giant, one that has lived a long stellar life and is now burning through its final chapters in spectacular style. The very thought that something like UY Scuti exists in the same universe we inhabit is humbling. It reminds us that no matter how vast Earth feels to us, its continents, its skies, its oceans, it's just a speck compared to the scale of what's out there. If our sun were the size of a common soccer ball, UY Scuti would be larger than a multi-story building. And that's not even hyperbole. It's a fact that we'll explore in staggering detail as we go deeper into its characteristics. This introduction isn't just to impress you with big numbers and distant wonders, it's to set the stage for a journey into understanding the extremes of nature. UY Scuti represents the upper limits of what a star can become before collapsing in on itself in one of the most violent events the universe can produce. And it's right there, a beacon in the depths of space, silently telling the story of stellar life, death, and the delicate balance between gravity and energy. It is, in short, the largest known star. But the true wonder isn't just in its size, it's in what that size means for our understanding of reality. Because when you start to put UY Scuti into perspective, you realize that our familiar measurements, kilometers, miles, light years, are woefully inadequate for conveying just how big and strange this object truly is. If we could step outside our solar system, out past the gravitational influence of the sun, beyond the icy realms of the Oort cloud, and look back at our home galaxy, the Milky Way, we would see a sprawling, spiral masterpiece. Within its vast arms and dense starfields lies a place where UY Scuti calls home, a relatively unassuming patch of sky from our perspective on Earth, yet a realm of extraordinary significance once you know what's hiding there. UY Scuti resides in the constellation Scutum, Latin for shield. Scutum is not among the most famous constellations. You won't find its name etched into the same cultural fabric as Orion or Ursa Major. It's modest in both size and brightness, made up of a small group of stars first introduced in the late 17th century by Polish astronomer Johannes Hevelius. Scutum stars don't blaze brilliantly in our skies, they form more of a quiet, shield-shaped pattern in the celestial tapestry. But, as is often the case in astronomy, appearances can be deceiving. Within this shield lies one of the most colossal stars humanity has ever laid eyes upon. From Earth's perspective, Scutum is best observed from the northern hemisphere during summer months, hanging in the rich band of the Milky Way between the constellations Sagittarius and Aquila. This region of the sky is particularly dense with stars because it points us toward the direction of the galactic center. And somewhere within that bright, crowded backdrop lies UY Scuti, shining faintly at an apparent magnitude of around +8.5, not visible to the naked eye, but detectable with even a small telescope. Now, here's where the scale gets staggering. UY Scuti is approximately 9,500 light-years away. 1 light-year is about 9.46 trillion kilometers, or roughly 5.88 trillion miles. So, if you wanted to hop in your fastest spacecraft, say, the Parker Solar Probe, which can travel at around 700,000 kilometers per hour, it would take you over 15 million years to reach UY Scuti. And that's assuming you could travel in a straight line at top speed without stopping, slowing down, or worrying about pesky things like fuel or radiation. Even though it's 9,500 light-years from us, in astronomical terms that's still relatively nearby within our galaxy, which spans about 100,000 light-years across. In fact, If the Milky Way were shrunk down to the size of North America, UY Scuti would be like living a few city blocks away compared to the vast expanse of the continent. That proximity is part of why we've been able to study it in such detail despite its faintness. UY Scuti sits in what astronomers call the Milky Way's Sagittarius arm, one of the spiral arms of our galaxy. This arm is a bustling stellar neighborhood, packed with gas clouds, young star clusters, and aging behemoths like UY Scuti. Its specific location is slightly above the galactic plane, which helps give us a clearer line of sight without too much intervening dust, though, as we'll discuss later, dust still plays a role in complicating measurements. If you wanted to find UY Scuti in the sky, you'd start by locating the bright star Altair in Aquila, then shift your gaze toward the dense star fields of Sagittarius, pausing in between to scan Scutum. With the right telescope, you'd see not a brilliant jewel but a reddish-orange glow, a deceptively soft light that belies its true enormity. The fact that we can pinpoint UY Scuti's position across thousands of trillions of kilometers speaks volumes about modern astronomy's precision. Through careful cataloging, parallax measurements, and spectral analysis, astronomers have mapped its location with remarkable accuracy. It's a bit like finding a single glowing ember in a campfire miles away, and then being able to measure exactly how far away it is. Its location in Scutum is also scientifically interesting because it's in a region rich with stellar evolution. There are other red supergiants, massive blue stars, and supernova remnants scattered through this area. That makes it a kind of stellar laboratory for understanding how stars live and die on extreme scales. And UY Scuti, sitting like an old monarch among these stellar siblings, offers a case study in the upper limits of star size before the inevitable collapse. Another fascinating point about its location is that, despite being in such a dense part of the galaxy, UY Scuti's brightness doesn't overwhelm our instruments. In fact, it appears dimmer than many much smaller stars closer to us. This is partly because of the inverse square law of light. Brightness decreases dramatically with distance. Even a giant like UY Scuti can be reduced to a faint speck from thousands of light-years away, especially when its light has to travel through dusty regions of the Milky Way that scatter and absorb some of its energy. When we consider its place in the universe, it's worth remembering that UY Scuti is just one among hundreds of billions of stars in the Milky Way alone, and our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. Yet, among all those countless points of light, this one stands out for its sheer size. The fact that it happens to sit in our own galaxy, in a location where we can study it, is nothing short of cosmic luck. In other words, UY Scuti isn't just floating randomly in space, it occupies a very specific position in the vast architecture of the Milky Way, a position that has allowed us to discover, measure, and marvel at it. If it were on the far side of the galaxy, hidden behind thicker curtains of dust and gas, we might never have known it existed. Instead, it sits in Scutum, quietly anchoring one of the most mind-bending facts in astronomy, that somewhere out there, a star so big it defies our intuition is slowly burning through its final fuel, preparing for the grand finale of its cosmic life. To understand UY Scuti, we have to understand what it means to be a red supergiant, a term that sounds impressive, but whose implications are even more extraordinary when unpacked. Stars, like people, go through life stages. Our Sun is currently in its stable main sequence phase, steadily fusing hydrogen into helium in its core. But a red supergiant like UY Scuti is in a much later chapter of its life. It's a star that started out far more massive than our Sun and has already burned through its hydrogen fuel at a breakneck pace. That fast burn rate is the hallmark of massive stars. They live fast, burn bright, and die young compared to smaller stars. When a star several times the Sun's mass exhausts the hydrogen in its core, gravity begins to pull inward while the core contracts and heats up. Hydrogen fusion shifts from the core to surrounding shells, and heavier elements, like helium, start fusing into carbon and oxygen. This internal restructuring releases enormous amounts of energy, and the star's outer layers respond by swelling outward, sometimes to hundreds or even over 1,000 times the Sun's diameter. This swelling is what transforms the star into a red supergiant. The red in red supergiant refers to the star's surface temperature and resulting color. Compared to the Sun's surface temperature of around 5,500 degrees Celsius 9,932 degrees Fahrenheit, UY Scuti's surface is relatively cool, about 3,300 degrees Celsius 5,972 degrees Fahrenheit. That cooler temperature shifts the peak of its light output toward the red end of the spectrum, giving it a deep, ruddy hue. But don't be fooled by the word cool. 3,300 degrees Celsius would still vaporize pretty much anything on Earth in a fraction of a second. This cooler temperature also means UY Scuti radiates light differently from our Sun. The Sun emits more light in the yellow and green parts of the spectrum, which combine to give us its familiar white appearance when viewed from space. UY Scuti, however, would appear as a soft, glowing ember, more like the warm light of a campfire than the harsh white of a midday sun. Then there's the supergiant part of the name. Red supergiants are among the largest stars in the universe by diameter, though not necessarily by mass. UY Scuti is the extreme example here, swelling to a size around 1,700 times the diameter of the Sun. If the Sun is a small orange in cosmic terms, UY Scuti would be a sphere as wide as a giant Ferris wheel, so massive in volume that its sheer dimensions challenge our ability to visualize it. The comparison gets even more dramatic when we consider how red supergiants are structured compared to the Sun. The Sun's outer layers are tightly bound by its gravity, making it relatively dense for a star. UY Scuti, on the other hand, is incredibly diffuse. Its outer atmosphere is a vast, tenuous cloud of gas that could be navigated by a spaceship without immediate destruction, assuming you could survive the radiation and heat. This thinness is why, despite its enormous size, UY Scuti is only about 30 times more massive than the Sun, an important point we'll delve into more deeply later. Red supergiants also have highly active surfaces. Their outer layers are in constant motion, stirred by massive convection currents that can be larger than the Earth itself. Imagine enormous, slow-moving storms of hot plasma, each one thousands of kilometers across, roiling across the star's face. These convection patterns, along with pulsations in the star's outer layers, cause variations in brightness over time, one of UY Scuti's defining characteristics. Our Sun, by contrast, is almost boring in its stability. It has sunspots and solar flares, yes, but its overall brightness and size remain essentially constant over centuries. UY Scuti, being in the final stages of stellar life, is much more chaotic. The processes going on inside it are unstable, and that instability shows up in its changing brightness, fluctuating size, and massive outflows of stellar material into space. Another point of comparison is lifespan. The Sun is a long-distance runner. It's expected to spend roughly 10 billion years in its main sequence phase. Red supergiants like UY Scuti, however, live comparatively short, intense lives. A star of UY Scuti's starting mass might only last 10 to 20 million years in total before exploding in a supernova. In cosmic terms, that's barely the blink of an eye. If the Sun were magically replaced by UY Scuti, our solar system would be utterly transformed. The star's immense size and heat would vaporize the inner planets entirely, and its cooler red light would bathe any surviving worlds in an eerie, dim glow. The habitable zone, the region where liquid water could exist, would be pushed out far beyond where Pluto currently orbits. But this replacement wouldn't last long. Red supergiants are ticking time bombs in astronomical terms, destined to collapse and explode. In short, UY Scuti's classification as a red supergiant tells us a lot about its past, present, and future. It's a star in the grand finale of its life, burning through heavier and heavier elements, expanding to a size that boggles the mind, and preparing for a final, spectacular exit from the stage. Compared to our Sun, it's cooler, redder, vastly larger, far more unstable, and dramatically shorter-lived. And yet, for all those differences, it's still subject to the same universal laws of physics that govern every star in the cosmos. A reminder that, in the end, the extraordinary is simply the ordinary taken to an extreme. If there's one image that truly drives home the scale of UY Scuti, it's imagining it sitting right where our Sun is now. We tend to think of the solar system as a roomy place. After all, there's about 150 million kilometers, 93 million miles, between Earth and the Sun. But if UY Scuti were to take the Sun's place at the center, roomy would no longer be part of our vocabulary. Let's start with the raw numbers. Our Sun has a diameter of about 1.39 million kilometers, 864,000 miles. UY Scuti's estimated diameter is around 2.4 billion kilometers, 1.5 billion miles. That's roughly 1,700 times larger. It's a leap so extreme that our brains resist it. We can picture something being twice as big, 10 times as big, maybe even 100 times, but 1,700 times? That's like replacing a tennis ball with a sphere bigger than a Ferris wheel, and then some. Here's what happens when you scale that up to the solar system. The orbit of Mercury, just 58 million kilometers from the Sun, would be swallowed whole inside UY Scuti. So would the orbit of Venus. Earth, 150 million kilometers from the Sun, would not only be gone but deep within the star's outer layers. Mars. Also inside. Even. The asteroid belt between Mars and Jupiter would vanish into UY Scuti's vast photosphere. The staggering part is that the star's surface would reach out almost to, or perhaps even beyond, the orbit of Jupiter, which is about 778 million kilometers, 484 million miles. From the Sun, Jupiter, the king of planets, would be skimming the outer layers of this monstrous star, possibly bathed in its superheated gases. Saturn, at over 1.4 billion kilometers away, might be one of the few planets to survive outside the star's actual surface, though still close enough to be baked and destabilized beyond recognition. In visual terms, imagine looking up from what would once have been Earth's position. Instead of seeing a bright disk in the sky that's small enough to be blinding, you'd see a colossal red surface filling nearly the entire dome of your vision, so close and so vast that the concept of a sky would cease to exist. There would be no day or night, no stars beyond, just the churning, glowing atmosphere of UY Scuti stretching to every horizon. This comparison also shows how much empty space there really is in our solar system. The Sun, though massive, is relatively compact compared to the distances between planets. UY Scuti, however, is the opposite, a giant, puffed-up balloon of plasma whose bulk fills what we normally think of as empty space. It's the difference between a streetlight in the middle of a field and a giant hot air balloon filling that same space. Now here's a subtle but important point. Just because UY Scuti's radius could extend past Jupiter's orbit doesn't mean it's solid all the way out. Stars don't have hard surfaces like planets. The outer regions of a red supergiant are extremely diffuse, thin enough that, technically, a spacecraft could travel through them without smashing into a wall. But the radiation, heat, and intense stellar winds would destroy anything long before it could get very far. So, in a sense, the edge of UY Scuti is more like a fog bank than a concrete wall, though this is a fog made of superheated plasma at thousands of degrees Celsius. Another mind-bending aspect is how this size changes the way we think about nearness in space. On Earth, Jupiter seems distant. Light from the Sun takes more than 43 minutes to reach it. But for UY Scuti, light from its center to the edge of its photosphere could take up to 7 hours to travel all the way around, a fact we'll dive into in detail later. If the Sun were that large, you could almost treat the outer edge of the solar system's inner planets as part of the star's atmosphere. Replacing the Sun with UY Scuti would also obliterate any chance of habitability for life as we know it. The habitable zone, where temperatures could allow liquid water, would be pushed so far out that even Pluto might be too warm. That's an astonishing reversal of how we usually think about heat in the outer solar system. In UY Scuti's system, cold would begin where interstellar space starts. And yet, for all this size, the star wouldn't feel dense in the way we imagine. If we could somehow scoop a spoonful of its outer layer, it would be far less dense than Earth's atmosphere at sea level. It's mostly empty space between atoms, held together by the star's gravity. This makes the comparison to our Sun even more striking. Our Sun is compact, stable, and relatively dense, while UY Scuti is enormous, tenuous, and unstable. So when we say it would extend beyond Jupiter's orbit, it's not just an astronomical curiosity, it's a complete rearrangement of how we perceive space in our neighborhood. A star like that sitting in our solar system would erase most of the planets we know, turn Jupiter into a skimmer at its edge, and stretch so far into the void that distances we once thought of as vast would be reduced to fractions of a stellar radius. Let's strip away the poetic imagery for a moment and stare directly at one of the most staggering raw measurements in all of astronomy, UY Scuti's diameter. When we say diameter in the context of a star, we're talking about the distance from one side of the star's visible surface to the other, measured straight through the center. For our Sun, that figure is about 1.39 million kilometers, 864,000 miles. That number is already beyond any human-built scale. If you could drive around the Sun's equator at highway speeds, it would take you years without stopping. But UY Scuti laughs at such modest numbers. Astronomers estimate its diameter to be roughly 2.4 billion kilometers, about 1.5 billion miles. That's not a typo. 2,400,000,000 kilometers from one edge to the other. It's a sphere so massive that you could lay 1,700 suns side by side across its width and still not cover the span of UY Scuti. To put that in another perspective, the distance from Earth to the Sun, what we call 1 astronomical unit, AU, is about 150 million kilometers. UY Scuti's radius, half its diameter, is over 1,200 million kilometers, or roughly $8. This means that if it replaced our Sun, its outer edge would sweep far past the asteroid belt and deep into the territory where Jupiter currently orbits, as we discussed earlier. Its sheer width would dominate the solar system in a way that's hard to visualize. Now, one might wonder, how do astronomers even measure something that big when it's 9,500 light-years away? The trick is they don't measure the diameter directly, they measure its angular size in the sky, how wide it appears from Earth, and then use its distance to calculate the actual size. This is like holding your thumb up to the moon. Your thumb looks like it's covering the moon, but we know the moon is much larger than your thumb, it's just farther away. For UY Scuti, the angular diameter is extremely small, fractions of an arcsecond, so astronomers use advanced techniques like interferometry, which combines the light from multiple telescopes to create a virtual supertelescope with higher resolution. This allows them to discern the star's apparent size despite the fact that it's just a faint point of light through most instruments. Once you combine angular size with distance, you get the figure that makes headlines, about 1,700 times the Sun's diameter. But here's where it gets tricky, this measurement is not absolute. Because UY Scuti is a red supergiant with a diffuse atmosphere, the surface isn't a sharp boundary like a planet's crust, it's a fuzzy, shifting layer where the gas becomes transparent enough for light to escape. Its pulsations and variable brightness also cause its apparent size to fluctuate over time. Even with those uncertainties, though, we can be confident that UY Scuti ranks at or near the top of the size charts. The only stars that rival it, like VY Canis Majoris or Stephenson 2-18, are in the same league, but UY Scuti's diameter remains one of the most extreme ever measured. Here's another way to think about the number. If you started at one side of UY Scuti and tried to fly across it in a modern jetliner traveling at around 900 km per hour, 560 miles per hour, you'd be on that trip for over 300 years without stopping. That's longer than the time between the Renaissance and today. And remember, that's just to go straight across, not to orbit it or fly around its circumference. Its circumference, by the way, would be almost 7.5 billion kilometers. So large that light itself, moving at about 300,000 kilometers per second, would take roughly 7 hours to complete the journey around it. Compare that to the Sun, where light circles it in just over 14 seconds, and you start to grasp just how dramatically bigger UY Scuti is. The number 1,700 times is so extreme that it forces you to rethink proportion entirely. On Earth, a difference of 1,700 in size is incomprehensible. If a person were 1,700 times taller than the average human, they'd be taller than Mount Everest. If a car were 1,700 times longer, it could stretch from New York to Los Angeles. And yet, UY Scuti achieves this ratio effortlessly in the most unforgiving environment we know, the vacuum of space. In astronomy, we often say that numbers stop being big at some point and start being absurd. UY Scuti's diameter is firmly in the absurd category, a measurement so massive it turns familiar distances into trivial footnotes. It's not just big, it's the kind of big that makes you question whether words are enough to capture the reality of the object itself. If UY Scuti's diameter makes your jaw drop, its volume will leave you in stunned silence. Because once you take that colossal diameter, about 1,700 times the Sun's, and imagine it in 3 dimensions, the scale leaps from incomprehensibly large to utterly mind-shattering. Volume isn't just about how far something stretches across. It's about how much space it encloses. And in 3-dimensional space, when you scale up an object's diameter, its volume increases by the cube of that scale factor. So if UY Scuti is about 1,700 times the Sun's diameter, you have to multiply 1,700 by 1,700 by 1,700 to see how much more volume it has. That's a factor of nearly 5 billion. Yes, You could fit approximately 5 billion suns inside UY Scuti. Not 5 million. Not 500 million. 5 billion. That's enough to fit our sun in there once for every human being currently living on Earth, plus a few 100 million spares. To visualize this, imagine the sun as a small orange. Now imagine filling a hollow sphere with oranges. If that sphere were UY Scuti's size, you'd need enough oranges to bury an entire continent several kilometers deep in fruit. The mind rebels at the image, because it's so far beyond anything we deal with in normal human experience. Let's try a different analogy. Our sun could swallow over 1 million Earths inside its volume. So, if UY Scuti could hold 5 billion suns, then it could theoretically contain about 5 quadrillion Earths. That's a 5 followed by 15 zeros. If each Earth were a marble, you could pile them up to form a mountain of glass spheres bigger than our solar system's inner planets combined. But here's where things get even stranger. Despite this mind-boggling volume, UY Scuti is not proportionally heavier. Remember, its mass is only around 30 times that of the Sun. That means the density of UY Scuti is incredibly low. Its outer layers are more like an extremely thin, hot fog than a solid object. You could travel through its outer atmosphere without ever hitting anything in the way we think of hitting matter, though you'd be instantly vaporized by the heat and radiation. The comparison also forces us to reconsider our mental picture of bigness in the universe. Volume is a deceptive measurement. Something that's twice as wide isn't just twice as big, it's 8 times the volume. In the case of UY Scuti, its enormous radius inflates the enclosed space to such an extreme that the mind almost loses track of the scale entirely. And this is where the 5 billion suns figure becomes both awe-inspiring and a little unsettling. Because stars are the engines of galaxies, their size, mass, and energy output dictate much of the environment around them. If you packed 5 billion suns worth of volume into one star, even if the mass isn't multiplied the same way, you've created an object so sprawling that its gravitational reach and radiation field would utterly dominate its local region of space. Imagine what it would look like from a nearby planet orbiting another star in the same galactic neighborhood. UY Scuti would not be a point of light in the night sky. It would be a colossal disk, perhaps even visible in daylight from that distance, stretching across a huge fraction of the heavens. Its bulk would make it seem almost like a wall in space, a physical boundary dividing the cosmos into this side and that side. One other point about the volume. Since red supergiants like UY Scuti are highly unstable and constantly shedding mass, a lot of that interior space is really a blend of gas layers at different temperatures, densities, and velocities. It's not like the Sun's relatively smooth layers. It's a roiling, turbulent, ever-shifting environment. Huge convective cells, each larger than Earth itself, rise and fall within that vast space. Pulsations in the star's outer shell cause it to expand and contract on timescales of months to years, meaning even the 5 billion suns figure is a moving target. Astronomers give these comparisons, like 5 billion suns, not because they expect us to truly grasp them, but because they're the best bridge we have between hard numbers and human imagination. Without such comparisons, the raw volume in cubic kilometers would be so absurdly large that it would be meaningless to most people. So here's the final takeaway. UY Scuti isn't just a big star, it's a structure of such staggering volume that, if the sun were a grain of sand, UY Scuti could be a beach stretching beyond the horizon. It is, in the most literal sense, cosmic excess, a reminder that nature, when left to the laws of physics, is capable of building things so outsized that even our wildest science fiction dreams seem modest. When we think of light, we think of speed, blinding, instantaneous speed. In the vacuum of space, light travels at roughly 299,792 kilometers per second, about 186,282 miles per second, a pace so quick that a beam could circle Earth more than 7 times in a single second. But even light, the ultimate cosmic sprinter, reveals something profound when you measure it against the scale of UY Scuti. Let's start with something familiar, our Sun. Its circumference, the distance all the way around its surface at the photosphere, is about 4.37 million kilometers, 2.71 million miles. Divide that by the speed of light and you get an astonishingly small number. It takes just over 14 seconds for light to travel once around the Sun. That means that from the moment a photon starts its journey around the Sun's visible edge, by the time you've taken a single breath, it's already completed the trip. Now let's scale that up to UY Scuti. With an estimated diameter of 2.4 billion kilometers, about 1.5 billion miles, its circumference is around 7.54 billion kilometers, 4.68 billion miles. That's not just a bigger number. It's so much bigger that the travel time for light balloons into the realm of hours. Do the math. \text time equals \frac 7 540 000 text kilometer 299 792 text approx 25 150 text seconds, and 25,150 seconds is roughly 7 hours. 7 hours for light. Think about that. Light, which could zip around Earth's equator over 26,000 times in that same period, would need the better part of a workday just to trace the outer rim of this single star. This comparison is more than just a number. It's an experience in scale. On human terms, if the Sun were a small stadium track, UY Scuti would be a marathon route stretching across entire countries. The fact that light, the universe's fastest traveler, is slowed not by friction or resistance but purely by distance tells you exactly how gargantuan this star really is. It's also a reminder that size isn't just about how many times bigger something is than another object. It's about how those differences compound in ways we don't instinctively feel. Going from 14 seconds to 7 hours is not a small step. It's a leap into an entirely different scale of existence. And here's where it gets even more staggering. Those 7 hours are just for light skimming the star's visible surface. Inside, things are far more complicated. A photon generated in UY Scuti's core would not travel straight to the surface. It would scatter off countless particles in the star's dense inner layers, bouncing around for possibly hundreds of thousands of years before escaping. That's true for our Sun as well, but in a star as large and diffuse as UY Scuti, that photon's meandering path could be even more epic, wandering across billions of kilometers of turbulent plasma before emerging into open space. If UY Scuti replaced our Sun and you could somehow ride a beam of light along its surface, you'd have time for lunch, a movie marathon, and maybe even a nap before completing your lap. That's not a race, it's a long-distance expedition. The 7-hour light travel time also provides another mental hook for the scale of the star. It's one thing to say it's 1,700 times the Sun's diameter. It's another to realize that something so immense exists within our galaxy that even light treats it as a serious journey. The cosmic speed limit feels less like an abstract number and more like a tangible measure of enormity when you see it stretched to hours instead of seconds. And here's an almost poetic detail. For us here on Earth, the light from UY Scuti takes about 9,500 years to reach us. That means the photons hitting your eyes when you look at it tonight, through a telescope, began their journey in the final days of the Stone Age, thousands of years before the pyramids were built. And yet, within the star itself, light could still spend centuries trapped before escaping. A slow crawl inside a giant, followed by a near-instant dash across the galaxy by comparison. So, the takeaway is simple but staggering. When we say UY Scuti is large enough that light needs 7 hours to go around it, we are saying it's so vast that the fastest thing in the universe can't treat it as a quick errand. That's the kind of cosmic scale that makes even the laws of physics feel stretched. When you first hear about UY Scuti's size, its 2.4 billion kilometer diameter, its ability to fit 5 billion suns inside, you might assume it must also be the heaviest, most gravitationally dominant object in its category. But here's the twist. Despite being the largest known star by volume, UY Scuti is only about 30 times more massive than our Sun. That seems almost contradictory, doesn't it? How can something so massive in size not be correspondingly massive in weight? The answer lies in the star's density, or rather, its lack of it. Our Sun is relatively compact. It packs its one solar mass, about 2 times 10 cubed kilograms, into a sphere only 1.39 million kilometers across. The result is an average density of about 1.41 grams per cubic centimeter, just a little denser than water. Inside, the density is much higher, with the core reaching over 150 grams per cubic centimeter due to extreme gravitational compression. Now imagine spreading that same mass out over a sphere 1,700 times wider. The density plummets. For UY Scuti, despite having 30 times the Sun's mass, its immense volume gives it an average density close to 10 grams per cubic centimeter in its outer layers. That's thinner than the best vacuum we can produce in laboratories on Earth. In other words, if you could somehow scoop up a chunk of UY Scuti's outer atmosphere the size of a beach ball, it would weigh almost nothing in your hand, though you'd never get the chance, because it would also be thousands of degrees Celsius and radiating deadly levels of energy. This low density is a natural consequence of the star's evolutionary stage. UY Scuti is a red supergiant, meaning it's in the final phases of its stellar life. In this stage, the core contracts as heavier elements fuse, but the outer layers expand enormously. Gravity's grip on these outer shells is weak compared to the intense outward pressure from the core's radiation, so the star puffs up into a vast, tenuous envelope of gas. Think of it like a giant soap bubble. The bubble may be enormous compared to the small drop of liquid that formed it, but the material is spread so thin that you could pass through most of it without encountering much resistance. UY Scuti is essentially a stellar bubble, with most of its volume occupied by almost empty space between particles. This also explains why the star is constantly shedding mass into space. The gravitational hold on those outer layers is so feeble that powerful stellar winds, streams of charged particles driven by the star's radiation, can carry away huge amounts of material over time. These winds create a halo of gas and dust around the star, which we can detect with telescopes sensitive to infrared light. Mass is the key driver of a star's fate, and here's where UY Scuti's modest mass, for its size, plays into its future. With about 30 solar masses, it started life as a massive blue star tens of millions of years ago. That mass is enough to guarantee a violent end, a core collapse supernova, but not so large that it would immediately collapse into a black hole without an explosive phase. When the end comes, its core will collapse under gravity's weight, triggering a catastrophic blast that will eject its remaining outer layers into space. The relatively low density also makes UY Scuti unstable. In such an inflated, thin atmosphere, small changes in pressure or temperature can cause large fluctuations in size and brightness. This is why it's classified as a pulsating variable star. Its outer layers literally swell and contract over time, like the slow breathing of a giant. For perspective, let's compare with a neutron star, which might have twice the Sun's mass packed into a sphere only about 20 kilometers across. While UY Scuti's density is so low it's almost a vacuum, a neutron star's density is so high that a single teaspoon of its material would weigh billions of tons. The difference between these two extremes is one of the most mind-bending contrasts in astrophysics. So the only 30 times the Sun's mass fact is a great reminder that bigger isn't always heavier. In the universe, size and mass don't scale together in the way we might expect from everyday life. A red supergiant can be so huge that light takes hours to circle it, yet be light enough, by stellar standards, to be considered modestly massive compared to much smaller but denser stars. And in UY Scuti's case, that relatively low mass spread across such a titanic volume is what gives it its ghostly, almost fragile nature. A fragile giant, destined to die in spectacular fashion, its massive frame a temporary inflation before gravity inevitably pulls it back in. Stars don't start their lives as titanic, inflated giants like UY Scuti. In fact, when UY Scuti was young, it would have looked nothing like it does now. It began as a massive, hot, blue star, brilliant, compact, and ferociously energetic. The transformation from that youthful, compact powerhouse into the enormous red supergiant we see today is the story of stellar evolution pushed to its extreme. The journey starts in a dense cloud of gas and dust, where gravity pulls material together until the pressure and temperature at the core become high enough for nuclear fusion to ignite. For UY Scuti, with an initial mass around 25 to 30 times that of the Sun, this ignition happened quickly by cosmic standards, likely within a few 100,000 years. As a young, massive star, it spent its main sequence phase fusing hydrogen into helium in its core. For smaller stars like the Sun, this phase can last billions of years, but for a star with UY Scuti's mass, it's brutally short, just a few million years. Why? Because fusion rates increase dramatically with mass. The more massive the star, the greater the gravitational compression in its core, and the higher the core temperature. That higher temperature supercharges fusion, turning hydrogen into helium at an extraordinary rate and burning through the fuel supply far faster than smaller stars. When the core hydrogen is exhausted, the star's life changes dramatically. With no hydrogen fusion in the core to provide outward pressure, gravity begins to win. The core contracts, heating up further, until it becomes hot enough for helium fusion to begin, converting helium into heavier elements like carbon and oxygen. This is the star's first major turning point. As the core shrinks and heats, the outer layers of the star react in the opposite way. They expand. And in massive stars like UY Scuti, this expansion is monumental. Hydrogen fusion continues in a shell surrounding the core, pumping out enormous amounts of energy that push the outer layers far, far away from the center. This expansion causes a dramatic drop in surface temperature, because the same energy is now spread across a vastly larger surface area, which shifts the star's color from blue-white to red-orange. This is why UY Scuti, once a hot blue star, now glows as a red supergiant with a surface temperature of around 3,300 degrees Celsius, much cooler than the Sun's 5,500 degrees Celsius. The outer atmosphere becomes incredibly diffuse during this stage. Gravity's hold on the extended layers is so weak that they can swell to enormous distances, sometimes more than 1,000 times the original diameter of the star. In UY Scuti's case, the expansion has pushed its visible radius out to over 1,200 million kilometers, big enough to engulf Jupiter's orbit if placed in our solar system. And this expansion isn't just a one-time event, it's a dynamic process. Red supergiants are unstable by nature. Their outer layers pulse, rising and falling in size over months or years as the balance between gravity and radiation pressure shifts. These pulsations are partly due to the fact that energy doesn't flow smoothly from the core. It comes in bursts as fusion rates fluctuate in the shells surrounding the core. Meanwhile, inside, the core continues its fusion journey, creating heavier and heavier elements: carbon, neon, oxygen, and eventually silicon. Each new fusion stage happens faster than the last. While hydrogen fusion lasted millions of years, helium fusion might last only hundreds of thousands of years. By the time the star is fusing silicon into iron, that phase will last mere days before the final collapse. Iron is the killer. Unlike lighter elements, fusing iron does not release energy, it actually consumes it. Once the core fills with iron, the delicate balance between outward fusion pressure and inward gravity collapses instantly. In less than a second, the core implodes under its own weight, triggering the catastrophic supernova that will end the star's life. But right now, UY Scuti is still in the late helium burning phase, possibly moving into carbon fusion. Its enormous size is the visible symptom of a star that has entered its final act, a brief, swollen existence before the inevitable collapse. Here's the poetic part: the very reason UY Scuti is so beautiful and grand, the reason it's so large, is also the reason it's doomed. That vast, glowing atmosphere exists because the core's life is nearly over, its energy output wildly unbalanced, forcing the star to swell in a last, magnificent gasp before the end. If we think of stars as living things, UY Scuti is in its sunset years. It's like an ancient tree whose trunk has hollowed, yet its branches spread wider than ever. Its size is not a sign of health or stability, but of imminent transformation, into something even more violent and spectacular. UY Scuti may be the largest known star, but it is far from a static, steady-burning beacon. It is a living, breathing giant, and I mean that almost literally. Its outer layers rhythmically expand and contract in cycles that cause noticeable changes in brightness when we observe it from Earth. This is what astronomers call a pulsating variable star. In UY Scuti's case, the variability is quite dramatic because of the nature of its outer atmosphere. Remember, we're not talking about a solid surface like Earth's crust. Stars have no surface at all. What we see as the star's outer edge is actually a region where the gases become transparent enough for photons to escape into space. In UY Scuti, this outer region is so diffuse and extended that even a small fluctuation in temperature or pressure can make it balloon outward or fall inward. When the outer layers expand, the star's surface area increases, and because its total energy output is spread over a larger area, the surface temperature drops slightly. A cooler star emits less light in the visible range, so to us, it appears dimmer. Conversely, when those layers contract, the surface gets a little hotter and the star appears brighter. These pulsations are not random, they are the result of a physical process known as the kappa mechanism. Here's how it works. Inside the star's atmosphere, certain layers are partially ionized, meaning the atoms have lost some of their electrons. These layers act like a kind of heat valve. When they absorb more energy, the ionization increases, trapping radiation and causing pressure to build up. This extra pressure pushes the layers outward. As they expand, they cool, allowing the trapped radiation to escape, which reduces the pressure and causes the layers to fall inward again. This cycle repeats, creating the observed pulsations. UY Scuti's pulsation period is around 740 days, just over 2 Earth years. That's the time it takes to complete one full cycle of expansion and contraction. Over that period, the star's brightness can vary by nearly a full magnitude in the visible spectrum, which is easily measurable with even modest telescopes. The size changes during these cycles are staggering by human standards. The star's radius can vary by tens of millions of kilometers during each pulsation. Imagine the Sun's size changing so much that Mercury's orbit was alternately engulfed and exposed every couple of years. That's the scale we're talking about. These pulsations also feed into another process, mass loss. Because UY Scuti's gravity is so weak at its outer edges, the motion of its pulsations can help fling gas and dust into space. Over time, this steady loss of material builds up a circumstellar envelope, a halo of gas and dust around the star. Infrared telescopes like NASA's Spitzer have been able to detect this shell, which glows faintly in the infrared as it absorbs and re-radiates the star's light. Interestingly, UY Scuti is classified as a semi-regular variable star, specifically SRC type, which means its pulsations are not perfectly uniform. The brightness variations generally follow a pattern, but there are irregularities, secondary pulsation modes, turbulence in the outer layers, and even the effects of giant convection cells the size of the star's radius. These convection cells, massive bubbles of hot plasma rising and falling, add a chaotic component to the star's light curve. Why do astronomers care about these pulsations? Because they act as a window into the star's interior. By studying the timing, amplitude, and irregularities of the light variations, astrophysicists can model the density, temperature, and composition of the layers inside. It's like using a stethoscope to listen to the heartbeat of a star. In the case of UY Scuti, the pulsations are a key clue to its evolutionary stage. The way the star breathes in and out tells us it's well into its late red supergiant phase, likely just a few 100,000 years, or even less, away from core collapse. In cosmic terms, that's practically the blink of an eye. There's also a poetic side to these pulsations. When you think of UY Scuti, don't picture a rigid, unmoving sphere in the sky. Picture a colossal, glowing ember, its outer layers drifting in and out like a slow cosmic tide. Every breath it takes carries it one step closer to the end of its life, and one step closer to a final, spectacular farewell. The story of UY Scuti's discovery begins not with space telescopes or advanced digital sensors, but in a very different era of astronomy, when meticulous human observation through refracting telescopes was the cutting edge of science. The year was 1860. Photography in astronomy was in its infancy, and most star catalogues were still compiled the old-fashioned way, by looking through an eyepiece and recording what you saw. At the Bonn Observatory in Germany, two astronomers, Adalbert Kruger and Carl Nikolaus Adalbert Schonfeld, were engaged in a massive project, mapping and cataloguing the stars visible from their location for what would become the Bonner Durchmusterung, BD, one of the most important star catalogues of the 19th century. This survey was an extraordinary undertaking. Using a 78mm refracting telescope, they painstakingly observed the sky strip by strip, measuring positions and estimating brightnesses by eye. When they came to the constellation Scutum, they noted a particularly bright, reddish star that caught their attention. At the time, they had no way of knowing it was anything unusual beyond its color and brightness. They recorded it in the BD catalogue as BD-12 degrees 5055, one star among hundreds of thousands listed. 4 decades, that's all UY Scuti was, just another entry in a star list, known primarily to professional astronomers and catalogue compilers. Its true nature as a pulsating variable and as one of the largest stars ever found wouldn't emerge until much later. The first hint that this was no ordinary red star came in the mid-20th century, when astronomers began systematically monitoring stellar brightness using photoelectric photometry, a far more sensitive method than visual estimates. In the 1950s and 1960s, data revealed that BD-12 degrees 5055 wasn't stable, it varied in brightness over time. This variability earned it an official variable star designation, UY Scuti, assigned by the General Catalogue of Variable Stars, GCVS. Still, even with its variable nature confirmed, no one yet suspected the full extent of its colossal size. That revelation had to wait for advances in interferometry, a technique where multiple telescopes are used together to measure tiny differences in the arrival times of light waves, allowing astronomers to directly measure the angular diameter of distant stars with unprecedented precision. In the early 2010s, a team of astronomers used a very large telescope, VLT, operated by the European Southern Observatory in Chile to observe UY Scuti. By combining interferometric data with accurate distance measurements from parallax methods, they were able to calculate its true physical size. The results stunned the scientific community. The star's radius was over 1,700 times that of the Sun, making it the largest known star at the time. This was one of those rare moments in science where a quiet, catalogued object from the 19th century suddenly becomes a headline grabber in the 21st. A star that had been sitting unnoticed in the sky, visible with even modest amateur telescopes, turned out to be one of the most extreme stellar giants in the Milky Way. From a humble entry in the Borner Durchmusterung to a modern astronomical celebrity, UY Scuti's story is also a reminder of how science builds upon itself. The early German astronomers in Bonn had no idea what they were looking at in 1860, but their precise cataloguing laid the foundation for discoveries more than 150 years later. And in a way, that's one of the most beautiful aspects of astronomy. The night sky is a constant canvas, but our understanding of it evolves with every generation. A dot of light in 1860 becomes the subject of awe and wonder in 2012, and perhaps in 2120, new technology will reveal even more about its mysteries. When it comes to measuring a star as absurdly huge as UY Scuti, we can't simply point a telescope and take a ruler to it. It's so far away, and so faint compared to nearby stars, that even the most powerful single telescope in the world would see it as nothing more than a tiny, blurred dot. This is where modern astronomy's cleverest techniques, interferometry and spectroscopy, step in to do the heavy lifting. Let's start with interferometry, because it's the key to understanding just how we got those jaw-dropping size estimates for UY Scuti. Interferometry works on a simple but powerful principle. If you take two or more telescopes and link them together so they collect light from the same target at precisely the same time, you can combine the data in such a way that the resulting image has the resolution of a telescope as large as the distance between them. In other words, you can create a virtual telescope the size of an entire observatory complex, or even larger if the telescopes are separated by kilometers. The Very Large Telescope Interferometer, VLTI, in Chile is one of the best tools we have for this job. It consists of 4 giant 8.2-meter telescopes and several smaller auxiliary ones that can be linked to work together. By combining their light, astronomers can measure the angular diameter of UY Scuti, the tiny angle it appears to span in the sky, usually measured in milliarcseconds. For reference, a milliarcsecond is about the apparent size of a penny viewed from more than 4,000 kilometers away. Once you have the angular size, you combine it with an accurate distance measurement, usually from parallax data gathered by missions like Gaia, to get the physical size. This is how astronomers arrived at the staggering figure of about 1,700 solar radii for UY Scuti. But size is only part of the story. To truly understand a star, we also need to know its temperature, composition, and motion. That's where spectroscopy comes in. Spectroscopy is essentially the science of decoding starlight. When the light from UY Scuti is passed through a spectrograph, it's spread out into a rainbow of colors, with dark absorption lines where specific wavelengths have been absorbed by atoms in the star's atmosphere. The exact pattern of these lines tells astronomers what elements are present, how hot the atmosphere is, and even how fast the star is moving toward or away from us, thanks to the Doppler effect. For UY Scuti, spectroscopy reveals that it's a cool, red supergiant with a surface temperature of around 3,300 degrees Celsius. It also shows evidence of heavy elements, carbon, oxygen, and nitrogen, that have been dredged up from the star's interior during its late-life fusion processes. This tells scientists that UY Scuti is far along in its stellar evolution and well on its way to a supernova fate. Spectroscopy also plays a role in tracking UY Scuti's pulsations. By taking repeated spectra over months and years, astronomers can see the star's outer layers moving in and out, shifting the absorption lines back and forth. This not only confirms the variability seen in photometry but also helps model the star's internal structure. What's truly remarkable is how precise these measurements have become. The margin of error for UY Scuti's diameter is still significant, partly because its distance is hard to nail down with absolute certainty, but the fact that we can estimate the size of an object nearly 9,500 light-years away to within a few hundred solar radii is nothing short of astonishing. It's worth remembering that all of this, interferometry, spectroscopy, photometry, requires not just powerful telescopes but also incredibly sophisticated computing. The raw data from an interferometer looks nothing like a picture. It's a complex pattern of interference fringes, light waves overlapping in constructive and destructive patterns. Only after careful calibration, data processing, and mathematical reconstruction do we arrive at a meaningful measurement. The same goes for spectroscopy. Those clean, colorful plots you see in astronomy textbooks are the end result of massive data correction processes, removing noise from Earth's atmosphere, calibrating wavelength scales with laboratory references, and compensating for instrumental quirks. So, when we talk about UY Scuti's mind-bending size, we're talking about the culmination of centuries of incremental scientific progress, from 19th-century astronomers writing down its position in a catalogue, to 21st-century observatories using kilometer-scale virtual telescopes to weigh and measure it with precision our ancestors couldn't have imagined. One of the most important things to understand about UY Scuti's largest star title is that it comes with a very big asterisk, because while the numbers we have are staggering, they're also estimates, not perfectly precise facts carved into cosmic stone. Astronomers have a good idea of its size, but there are layers of uncertainty baked into the measurement, and each layer can nudge the final figure up or down, sometimes by a surprisingly large amount. The first and perhaps biggest source of uncertainty is distance. UY Scuti is about 9,500 light-years away. At least, that's the best estimate we have from current parallax measurements. Parallax works a bit like holding your finger in front of your face and closing one eye, then the other. The apparent shift tells you how far away the object is. For stars, we measure this shift as Earth orbits the Sun, using high-precision instruments like ESA's Gaia spacecraft. The problem is, at thousands of light-years away, the parallax shift is incredibly small, fractions of a milliarcsecond, and interstellar dust between us and UY Scuti can scatter and dim its light, complicating the measurement even more. If the distance turns out to be even a little different than we think, the calculated diameter could shift by hundreds of solar radii. The second challenge comes from brightness variations. UY Scuti is a pulsating variable star, which means its outer layers expand and contract rhythmically over time. This causes changes in its brightness and even its apparent angular size when viewed from Earth. If you measure it at one phase of its pulsation cycle, you might get a slightly different number than if you measured it at another. Third, there's the atmospheric haze problem. Not our atmosphere, but UY Scuti's. Red supergiants have vast, extended atmospheres filled with gas and dust, which scatter light in complex ways. The surface of such a star isn't a hard, well-defined edge like a planet's. Instead, it's a fuzzy gradient from hot, dense plasma to cooler, more diffuse gas. When astronomers talk about the radius of UY Scuti, they have to decide where along that gradient they're drawing the line. Depending on the wavelength of light being observed, visible, infrared, or radio, the apparent size can change. Interferometry helps with precision, but even then, the limb darkening effect, where the edges of the star appear dimmer than the center, can make defining the true diameter a bit of an art. This is why you might see slightly different numbers for UY Scuti's size in different scientific papers. In fact, there's still an ongoing debate about whether UY Scuti truly deserves the crown as the largest star known. Some measurements suggest it might be slightly smaller than previously thought, perhaps closer to 1,500 solar radii instead of over 1,700. On the flip side, other candidates like Stephenson 2 to 18 might actually be larger if their distances are confirmed with greater accuracy. This uncertainty isn't a flaw in science. It's science working exactly as it should. Every new measurement helps refine the picture. In the past, when distance estimates were less accurate, some stars seemed to be absurdly huge, only for later data to bring them back down to more reasonable sizes. UY Scuti's status could change in the future, not because our tools fail, but because they get better. In other words, think of UY Scuti's 1,700 times the Sun's diameter figure as our best current approximation, rather than an eternal, immutable truth. Future missions, like the next Gaia data releases, more powerful interferometers, and advanced space telescopes, could sharpen that figure further, or even move it out of first place entirely. What's remarkable, though, is that no matter where UY Scuti ends up in the rankings, it will still remain among the most titanic stars humanity has ever measured. Whether it's 1,500 or 1,700 solar radii, the difference is trivial compared to the incomprehensible vastness it represents. Let's imagine, just for a moment, that UY Scuti suddenly swapped places with our Sun. No cosmic warning, no gentle transition. One day you wake up, look out the window, and in place of our familiar golden disk in the sky, there's a colossal, fiery red monster filling almost the entire horizon. The very first thing you'd notice is that daytime wouldn't look anything like it does now. In fact, it wouldn't just be daytime, it would be an unending, overpowering, hellish glare. If UY Scuti sat at the center of our solar system, its outer edge wouldn't stop at Mercury, Venus, or even Earth. It would engulf all of those and keep going. At its current estimated size of around 1,700 solar radii, its surface would extend beyond the orbit of Jupiter. That means Earth wouldn't be a cozy blue marble orbiting at a safe distance, we'd be inside the star itself. From our perspective here on the surface, if surface even existed in this scenario, the concept of sky as we know it would vanish. Instead of seeing a small circle of light against black space, you would see endless fiery reds, oranges, and darker patches caused by gigantic convective cells, bubbling regions of hotter and cooler plasma. These patches could be larger than Earth themselves. You'd also see massive arcs of gas being blown away by stellar winds, shimmering and shifting in slow, majestic motion. The brightness would be so intense that no living thing as we know it could survive. UY Scuti's luminosity is hundreds of thousands of times greater than the Sun's, so the energy pouring down would vaporize our oceans in moments, strip away the atmosphere almost instantly, and melt the surface crust into a molten sea. And here's a strange twist. Despite its overwhelming size and luminosity, the star's color wouldn't be white-hot like the Sun's, but a deep orange-red, because of its cooler surface temperature, (-3 300 degrees C compared to the Sun's (-5 500 degrees C). So the sky would glow like a perpetual sunset, except that it would be bright enough to blind you instantly. The night sky would also change dramatically, not because of starlight, but because there would be no night. UY Scuti would be so large in our sky that even if Earth could somehow exist outside of it, say, orbiting just beyond its swollen surface, its angular size would cover a huge portion of the sky. Stars behind it would be blocked out entirely, and space would seem smaller, swallowed by the bloated red behemoth dominating our view. If you were on a hypothetical spacecraft orbiting near Earth's current position, you'd see something even more surreal. UY Scuti looming so large that the curvature of its surface would be almost imperceptible. It would feel less like orbiting a star and more like hovering next to an endless glowing wall. There's also an eerie psychological factor. Our Sun, small as it appears in the sky, already feels vast and powerful when you consider its true size and energy. But seeing UY Scuti up close would be an almost existential experience. It would strip away any illusions we have about humanity's scale in the universe. You wouldn't be looking at a star in the distance. You'd be staring into a cosmic furnace so massive that the very concept of here and there blurs at its edges. Of course, the practical reality is that this scenario is utterly impossible without destroying the solar system. A star like UY Scuti would swallow the inner planets whole and fundamentally reshape the outer ones. Jupiter and Saturn's moons, if they remained, would experience wild gravitational and thermal effects. The delicate orbital ballet of our solar system would be shattered in an instant. Still, it's fascinating to think about, because when you picture UY Scuti at the Sun's distance, the numbers stop being abstract and start feeling visceral. It's one thing to hear 1,700 times the Sun's diameter, and another to imagine a sky where the star's edge stretches from horizon to horizon, making you feel as if the entire universe is aflame. When we imagine the largest star in the universe, our instinct is to picture something not just bigger, but hotter, a raging inferno that burns brighter and fiercer than anything we've ever seen. But in UY Scuti's case, size doesn't go hand in hand with blistering surface heat. In fact, despite its monstrous scale and staggering luminosity, UY Scuti is actually cooler at its surface than our relatively modest Sun. The Sun's surface temperature, more precisely, its photosphere, sits at around 5,500 degrees Celsius, about 9,932 degrees Fahrenheit. That's hot enough to emit a bright yellow-white light that appears golden in our sky. UY Scuti, on the other hand, has a surface temperature of roughly 3,300 degrees Celsius, about 5,972 degrees Fahrenheit. In human terms, that's still far beyond anything we could comprehend touching, but in stellar terms, it's a significantly cooler outer layer. This temperature difference is one of the main reasons UY Scuti has its distinctive reddish-orange glow. Stars obey a general rule: hotter stars appear blue-white, cooler stars appear red-orange. Since UY Scuti is a red supergiant, its cooler temperature shifts its light output toward the red end of the spectrum. It's not that the star is cold, it's still thousands of degrees hot, but compared to other stars, it radiates more of its energy in longer, redder wavelengths. Here's where things get fascinating. That lower temperature might make you think UY Scuti is less luminous than the Sun, but the opposite is true. Luminosity isn't just about temperature, it's also about surface area. And when your surface area is mind-bogglingly vast, over 3 billion times greater than the Sun's, you can still outshine it by hundreds of thousands of times despite being cooler. This is why UY Scuti can be seen across thousands of light-years even though it glows with a softer hue than our Sun. The relatively cool temperature is a direct result of its red supergiant stage. In this late stage of stellar evolution, the outer layers of the star expand massively, causing the energy to be spread across a much larger surface area. Think of it like this: a small heating element will glow white-hot, but if you stretch that same heat over a huge surface, it will appear cooler in color, more orange or red, even if the total amount of energy it's giving off is much greater. Another interesting side effect of this temperature is how UY Scuti interacts with its surroundings. At 3,300 degrees Celsius, the star's outer layers aren't tightly bound. The low surface gravity, due to the star's massive radius, means that gas and plasma can be lost into space relatively easily. This is part of why red supergiants like UY Scuti shed so much material into their surroundings, forming clouds of dust and gas that can obscure parts of the star from our view. If you were to somehow observe UY Scuti's surface up close, it wouldn't be a smooth, consistent sphere. Instead, you'd see enormous convective cells, hotter, brighter patches and cooler, dimmer patches, moving sluggishly across its photosphere. Because the temperature is lower than that of smaller, denser stars, these cells can grow absolutely gigantic, each one spanning tens of millions of kilometers. It's worth noting that cooler surface temperatures don't mean a cooler interior. Deep within, UY Scuti's core is still a nuclear furnace fusing heavy elements, with temperatures climbing into the tens of millions of degrees. The outer layers may be cooler, but the heart of this star remains unimaginably hot and powerful, the engine driving its immense luminosity and size. So while the Sun might be hotter in the outer layers, UY Scuti's sheer immensity and energy output leave our star looking tame by comparison. Its cooler red-orange glow is a mark of age, size, and the fascinating physics that occur when a star swells to truly colossal proportions. Here's where the true paradox of UY Scuti comes into focus. Despite having a surface temperature significantly cooler than our Sun, this star absolutely dwarfs the Sun's brightness and energy output. This isn't just a little brighter situation, this is on a completely different scale, almost incomprehensible when you try to put it into human terms. Let's start with a simple but profound truth in astrophysics. A star's total energy output, or luminosity, is determined not only by its surface temperature but also by the size of its surface area. The Sun, with its surface temperature of about 5,500 degrees Celsius, radiates a tremendous amount of energy from every square meter. Multiply that by the Sun's total surface area, and you get our familiar, life-sustaining solar energy. But UY Scuti? It has more than 3 billion times the Sun's surface area. Even though each individual square meter of UY Scuti's surface is cooler and radiates slightly less energy than the Sun's, the sheer enormity of its surface makes its total output staggeringly high. Current estimates suggest that UY Scuti shines with a luminosity roughly 340,000 times greater than the Sun's. That means if you replaced our Sun with UY Scuti, without changing Earth's orbit, we'd receive hundreds of thousands of times more energy than we currently do. That's not a matter of a little extra warmth. It would turn our planet into a vaporized husk in an instant. The oceans boiled away. The crust melted. Atmosphere gone in a flash. Another way to picture it, The sun emits enough energy each second to power human civilization for millions of years if we could capture it all. UY Scuti emits that much energy multiplied by hundreds of thousands every single second, without pause, across every wavelength from visible light to infrared radiation. This level of luminosity is possible because of the way energy is generated and transported in massive stars. Deep within UY Scuti, the core is fusing heavier and heavier elements as it nears the end of its life. The energy produced there must fight its way outward, pushing against the star's massive gravitational field. But because UY Scuti is so puffed up, its outer layers are spread thin, and the photons can escape more easily than in a compact star. This combination of intense core activity and enormous surface area produces the mind-bending glow we observe across nearly 10,000 light-years. Even its color plays a role in our perception of brightness. While UY Scuti's red-orange hue makes it look cooler than the sun in photographs, the reality is that it's radiating an immense amount of energy in the infrared spectrum, wavelengths we can't see with our eyes but can detect with specialized instruments. Infrared output is a hallmark of red supergiants, and UY Scuti floods the cosmos with it. If you were anywhere within a few dozen light-years of UY Scuti, it would dominate your night sky. Even from that distance, it could appear brighter than our moon appears to us. The heat and light from such a star would dramatically alter the conditions of nearby planets and potentially strip atmospheres from moons or smaller worlds. One of the most awe-inspiring facts is that this intense energy production is also its doom. Massive stars burn through their fuel far faster than smaller stars like the Sun. While our Sun is expected to live for around 10 billion years, UY Scuti will have lived only a fraction of that, mere millions of years, before exhausting its fuel and collapsing into a supernova. It's a vivid reminder that in the stellar world, burning brighter often means burning out sooner. So yes, UY Scuti is cooler at its surface than our Sun. But in the cosmic balance sheet of energy, temperature is only half the equation, and size, in this case, more than makes up for the difference. This is why UY Scuti can be visible from across such immense distances, a lone beacon of furious energy in the Scutum constellation. When a star swells into a red supergiant, it's not just a quiet, graceful expansion. It's messy, chaotic, even, and UY Scuti is no exception. Surrounding this cosmic colossus is a vast and complex environment made of gas, dust, and stellar wind, all of which have been thrown off during its late-stage life. This envelope of material is like a record of its recent history, each layer telling the story of powerful outflows and mass loss. Right now, UY Scuti is in a phase of stellar evolution where its outer layers are loosely bound by gravity. With such a massive radius, the surface gravity at its photosphere is extraordinarily weak compared to our Sun. That means that the turbulent convection currents inside the star, those gigantic, boiling cells of hot plasma, can easily push material outward. Add to that the star's pulsations, those rhythmic expansions and contractions we talked about earlier, and you have a recipe for matter being ejected into space in colossal amounts. Astronomers have observed that red supergiants like UY Scuti can lose billions of tons of material each year. This isn't a steady stream, like a gentle breeze. It's more like irregular gusts and waves of stellar wind, varying in intensity over time. These stellar winds carry gas, mostly hydrogen and helium, but also heavier elements forged in the star's fusion furnace, away from the surface and into the surrounding space. As this gas travels outward, it cools and begins to condense into dust grains. Over decades, centuries, and millennia, these particles form a dusty shell around the star, which can stretch for many astronomical units, the distance from Earth to the Sun, in every direction. In the case of UY Scuti, infrared observations have revealed such an envelope, glowing faintly from the heat of the star's light. This dusty cloak is important for two reasons. 1. It hides parts of the star from view. The dust can absorb visible light, making the star appear dimmer in certain wavelengths and complicating measurements of its true size and luminosity. 2. It enriches the galaxy. That dust contains elements like carbon, oxygen, silicon, and magnesium, key building blocks for planets, asteroids, and, eventually, life. When UY Scuti finally goes supernova, all of this material will be hurled even farther into space, seeding the interstellar medium with heavy elements that future generations of stars and planets will inherit. The surrounding space around UY Scuti is also turbulent. Gas ejected from the star interacts with interstellar gas and magnetic fields, creating complex shock fronts and waves. Imagine ripples in a pond after you toss in a boulder. Only here, the boulder is a supersonic stream of star stuff. These collisions heat the surrounding gas, making the entire region around UY Scuti glow in different wavelengths, from infrared to radio. Some of the dust clouds are thick enough to obscure background stars when viewed from Earth. If you could look at UY Scuti through a powerful telescope sensitive to infrared light, you'd see the star sitting at the center of a hazy cocoon, almost like a lantern in fog. That fog is made of material the star itself has been shedding for thousands of years. One remarkable implication of this mass loss is that it directly shapes the kind of supernova UY Scuti will produce. The more mass it loses now, the lighter its outer envelope will be when the core finally collapses. That, in turn, affects the brightness, duration, and even color of the eventual explosion. Some red supergiants that shed a lot of material before going supernova produce a spectacular interaction when the explosion shockwave slams into that dense cloud of gas and dust, creating a bright, long-lasting display. In short, UY Scuti isn't just sitting quietly in the void, it's actively sculpting the space around it, one colossal exhalation at a time. And the gas and dust drifting in that region today will one day be recycled into entirely new worlds, making UY Scuti's legacy far more than just its size or brightness. If there's one thing UY Scuti's colossal size tells us loud and clear, it's that this star is living on borrowed time. In the grand timescale of the universe, where stars can live for billions of years, UY Scuti's remaining lifespan is little more than the blink of an eye. Astronomers estimate that it is firmly in the late stages of its stellar life cycle, with perhaps less than 1 million years left before it ends in a cataclysmic supernova. And in cosmic terms, 1 million years is next to nothing. It's like knowing a tree will fall sometime in the next 5 seconds of your life. The reason for this short lifespan lies in the nature of massive stars. While smaller stars like our Sun burn their nuclear fuel slowly and efficiently, massive stars like UY Scuti live fast and die young. They generate enormous amounts of energy in their cores, which requires burning through hydrogen, helium, and eventually heavier elements at a ferocious rate. The more massive the star, the more intense the fusion process, and the faster it uses up its nuclear fuel. Right now, UY Scuti has already burned through most of its hydrogen in the core. It's likely fusing helium into carbon and oxygen, and possibly beginning the fusion of heavier elements in layers around its core. This onion-like structure, where different shells of the star are fusing different elements, is a hallmark of stars in their final evolutionary stages. The problem is, the heavier the element being fused, the less energy the process releases, and the faster it runs out of fuel for that layer. Eventually, the fusion process will reach iron in the core, and that's where the clock hits zero. Iron fusion doesn't produce energy, it consumes it. Without the outward push from fusion to counteract gravity, the star's core will collapse under its own immense weight in a fraction of a second. This collapse will trigger an enormous rebound effect, sending a shockwave through the star's outer layers and blowing it apart in a brilliant supernova. When we say less than 1 million years, keep in mind that for UY Scuti, the final stages could happen even sooner. The variability we've observed, its pulsations and mass loss, are signs that it's unstable, a cosmic giant already staggering under its own bulk. Some red supergiants survive in this phase for hundreds of thousands of years. Others transition to more extreme phases like yellow hypergiants or luminous blue variables before exploding, a process that can shorten their remaining lifetime significantly. For humanity, the good news is that UY Scuti's eventual supernova poses no danger to Earth. At roughly 9,500 light-years away, it's too distant for harmful radiation or particles from the explosion to directly affect us. Still, when it happens, the event will be one of the most spectacular astronomical sights in human history, visible even in daylight and casting shadows at night. But for UY Scuti itself, the end will be sudden and absolute. The star we see today, a bloated, glowing titan, will be gone, replaced in a matter of days by an expanding cloud of gas and dust, and possibly a neutron star or black hole at its core. Its life will end violently, but its death will enrich the galaxy with heavy elements, seeding the next generation of stars and planets. In a way, UY Scuti's life expectancy is a bittersweet fact. On one hand, we're witnessing a star in a rare and fleeting stage of existence. On the other, we know that the very traits that make it extraordinary are also signs of its imminent demise. We are lucky, in this vast cosmic timeline, to exist at a moment when UY Scuti is still here for us to study and marvel at, because on the universal clock, it's seconds away from midnight. When UY Scuti finally reaches the end of its life and detonates as a supernova, the event will not be the final chapter in its story, rather, it will be the transition to its ultimate form. What happens in the aftermath depends largely on the exact mass of the star's core when it collapses, but in every scenario, we're looking at the creation of one of the most exotic objects in the universe. At the moment of core collapse, gravity will overwhelm everything. The once vast, diffuse layers of UY Scuti's atmosphere, spanning billions of kilometers, will be flung outward into space at a significant fraction of the speed of light, forming a brilliantly luminous shell of gas. The outer layers will be shredded, glowing from the immense heat and shockwaves, and over the following weeks to months, that supernova remnant will fade into the darkness, expanding into the interstellar medium. But deep inside, the fate of UY Scuti's core will be sealed in a fraction of a second. If the remaining mass of the collapsed core is below a certain threshold, about 2 to 3 times the mass of the Sun, then the crush of gravity will halt when neutron degeneracy pressure kicks in. In that case, the result will be a neutron star. A neutron star is essentially a stellar corpse made almost entirely of neutrons, packed so densely that a single teaspoon of its material would weigh as much as a mountain. Despite containing more mass than our Sun, a neutron star would be only about 20 kilometers in diameter, a sphere small enough to fit inside a city, yet possessing gravity so intense that nothing on its surface could survive for more than a fraction of a second. If UY Scuti's rotation rate survives the collapse, this neutron star could become a pulsar, blasting beams of radiation across space like a cosmic lighthouse. However, there's a very real chance that UY Scuti's core is too massive for even neutron degeneracy pressure to withstand. If the collapsing core is above that critical mass, the gravity will keep pulling inward, compressing the core to a point of infinite density, a singularity, creating a black hole. If that happens, no force in the universe will be able to stop the collapse, and even light will be trapped inside the event horizon. If UY Scuti becomes a black hole, it will likely be a stellar mass black hole, perhaps 5 to 15 times the mass of our Sun, depending on how much material is lost during the explosion. This black hole would be invisible directly, but we might detect it by the X-rays and other radiation produced as nearby gas and dust spiral into it, heated to extreme temperatures by its gravity. In either outcome, neutron star or black hole, the supernova's debris cloud will continue to expand, carrying with it the elements forged inside UY Scuti's core over millions of years. Carbon, oxygen, silicon, magnesium, calcium, and iron, ingredients for planets, oceans, atmospheres, and even living organisms, will be scattered across hundreds of light-years over time. This is one of the great cosmic ironies. The death of a star can sow the seeds of future life. The visual aftermath in the night sky would be extraordinary. For centuries, perhaps millennia, the glowing remnant would be visible in telescopes, similar to the Crab Nebula, which is the remains of a supernova observed on Earth in 1054 CE. Astronomers of the future might even trace the expanding shell of gas back to a point in the sky where UY Scuti once shone. What's perhaps most humbling is the knowledge that the supernova aftermath will outlive UY Scuti's actual life by orders of magnitude. The star may have existed for just a few million years, a mere heartbeat in cosmic time, but its remnants, whether neutron star or black hole, could persist for billions of years, quietly marking the spot where the largest star we have ever found once burned. When UY Scuti finally blows, it won't just vanish quietly into the dark, it will shake the very fabric of its local galactic neighborhood. A supernova of this magnitude is one of the most energetic events in the universe, releasing more energy in a few weeks than our Sun will emit over its entire 10 billion-year lifetime. The blast will send a shockwave of high-energy particles, radiation, and stellar debris hurtling outward at thousands of kilometers per second. For nearby star systems, those within a few dozen light-years, the impact would be dramatic. Any planets unlucky enough to be orbiting stars close to UY Scuti could be scorched by intense radiation and stripped of their atmospheres. Gamma rays, X-rays, and charged particles from the supernova would batter their worlds, potentially sterilizing any life that existed there. The shockwave itself would be like a cosmic snowplow, ramming into clouds of gas and dust in the interstellar medium. This collision can have two very different effects. In some cases, The shockwave will destroy delicate molecular clouds, dispersing the material before it can clump together to form new stars. In other cases, the pressure from the expanding shockwave actually compresses gas clouds, triggering the birth of new stars and planetary systems. In that way, UY Scuti's death could ironically help seed new generations of suns and worlds. Astronomers have long suspected that nearby supernovae in Earth's past may have influenced our planet's environment and even driven mass extinctions by altering atmospheric chemistry. The leading hypothesis for one such event about 2.6 million years ago suggests a supernova within 150 light-years of Earth may have bombarded our planet with cosmic rays, potentially cooling the climate and increasing mutation rates in life forms. But here's the good news: UY Scuti is far too distant, around 9,500 light-years away, to cause any direct harm to Earth. Even so, the energy it will release will still spread across interstellar space, and some of it might eventually reach our solar system, though diluted to harmless levels by the time it arrives. Closer to home for UY Scuti itself, the devastation will be immediate. Any planets orbiting it, if any could exist around such an unstable star, would be obliterated instantly. Any companion stars in a binary system could be blasted with intense heat and stripped of their outer layers, altering their own evolutionary paths. The expanding supernova remnant will continue to interact with the surrounding environment for tens of thousands of years, lighting up the region in glowing tendrils of ionized gas. Future civilizations with telescopes in that part of the galaxy will see a beautiful, chaotic nebula, a direct legacy of UY Scuti's final act. In the bigger picture, UY Scuti supernova will be just one note in the ongoing symphony of stellar life and death in our galaxy. But it will be a loud one, reshaping its corner of the Milky Way, redistributing heavy elements, and possibly giving rise to entirely new star systems that, billions of years from now, might themselves host planets where intelligent beings gaze up at their sky and wonder about the giant star that once exploded nearby. In the cosmic contest of who's the biggest, UY Scuti has worn the crown for years in popular astronomy discussions, but it's not alone among the titans of the universe. To appreciate just how staggering its size is, it helps to compare it with other colossal stars we've studied. Names like Betelgeuse, VY Canis Majoris, and Stephenson 2-18. Let's start with Betelgeuse, the famous red supergiant in the constellation Orion. Betelgeuse is a celebrity in the night sky, bright, easy to spot, and the subject of endless speculation about when it might go supernova. Its diameter is estimated to be around 764 times that of the Sun, which is massive by any standard. If placed at the center of our solar system, Betelgeuse's surface would extend past the orbit of Mars and perhaps approach Jupiter's asteroid belt region. Yet, despite its fame, Betelgeuse is still only about half the size of UY Scuti. That's like comparing a skyscraper to a mountain. It's big, but it's not that big. Next up, VY Canis Majoris, another red supergiant that, for a time, was considered the largest known star. Early estimates placed it at about 1,500 to 1,800 times the Sun's diameter, which would put it roughly on par with UY Scuti. However, more refined measurements suggest it's probably closer to 1,420 solar diameters, still gigantic but not quite a record-breaker. VY Canis Majoris is also noteworthy for its enormous mass loss rate. It's shedding vast amounts of material into space, creating a complex nebula that makes it difficult to measure precisely. Then there's Stephenson 2-18, a relatively new contender in the record books. Discovered within the massive Stephenson 2 star cluster, it's estimated to be up to 2,150 times the Sun's diameter, which, if confirmed, would make it even larger than UY Scuti. Stephenson 2-18's potential record-breaking size reminds us that the largest known star title is far from permanent. As our measurement techniques improve and as we find new candidates in dust-shrouded regions of the galaxy, the leaderboard changes. In terms of volume, these giants all share one trait: they could swallow our Sun billions of times over. But the jump in size from one to another is mind-bending. If Betelgeuse were a basketball, UY Scuti would be a beach ball, and Stephenson 2-18 would be a small planet in comparison. The human brain struggles to truly visualize these scales, because even the smaller of these giants are so far beyond anything in our direct experience. One interesting takeaway from these comparisons is that these stars, despite their different sizes, all fall into the red supergiant category, meaning they share similar late-life evolutionary processes. Their differences in size come from a mix of original mass, metallicity, chemical composition, and the timing of when we happen to observe them in their evolutionary cycle. So while UY Scuti remains one of the champions in terms of sheer diameter, it exists in a league filled with other titanic players, each one a fascinating laboratory for studying stellar physics, mass loss, and the final stages of stellar evolution. And every time we refine our data or spot a new candidate in some dusty corner of the galaxy, the balance of power in this oversized club can shift dramatically. The title of largest star ever found is not carved into cosmic stone. It's more like a temporary crown that keeps passing from one contender to another as our understanding of the universe deepens. UY Scuti may hold the title in many discussions today, but the very nature of how we discover and measure stars guarantees that the record will change, perhaps many times in our lifetime. There are a few major reasons for this shifting leaderboard, and they all come down to a mix of astronomical technology, observational challenges, and the dynamic nature of stars themselves. First, measurement techniques are constantly improving. A century ago, astronomers relied solely on brightness estimates and rudimentary parallax measurements to gauge a star's distance and size. Now, we have tools like optical interferometry, which lets us combine the light from multiple telescopes to effectively create a telescope the size of a football field, allowing unprecedented resolution. We also use spectroscopy, which analyzes the light from a star to deduce its temperature, surface composition, and motion. Each technological leap gives us more precise size estimates, and sometimes those estimates shrink a star that once looked enormous. Second, many of the largest stars are shrouded in dust. Red supergiants, in particular, shed huge amounts of mass in the form of gas and dust as they approach the end of their lives. This dusty veil can obscure the star and distort our readings. Sometimes we initially overestimate a star's size because we're measuring the glow of the dust cloud rather than the actual stellar surface. When infrared or radio observations cut through that dust, we may find the star is smaller, or sometimes larger, than we thought. Third, distance estimation is tricky, especially for stars thousands of light years away. If we think a star is farther than it actually is, we'll calculate a bigger radius for it based on its apparent brightness. Improvements in parallax measurements, thanks to missions like ESA's Gaia Space Observatory, often lead to recalibrations of size estimates. Gaia's data has already caused several famous largest star candidates to lose their crown when we realized they weren't as far away, and therefore not as massive as we thought. Fourth, stars like UY Scuti are variable. Their outer layers pulsate, causing their size to change over months or years. That means a measurement taken during one part of the pulsation cycle might give a very different radius than a measurement taken later. If we only catch a star at its most inflated moment, we might crown it the largest, only to later realize it was temporarily puffed up. Lastly, and perhaps most excitingly, the Milky Way is still hiding giants we haven't found yet. Many enormous stars live in dense, dusty star-forming regions where visible light can't penetrate. Only in recent decades, with the advent of infrared astronomy, have we begun peering into these obscured nurseries and finding truly colossal stars, like Stephenson 2-18, lurking there. There may be even bigger ones out there, completely invisible to our optical telescopes but waiting to be revealed by the next generation of observatories. So when we say UY Scuti is the largest star ever found, we have to mentally add an asterisk, so far, based on what we can see and measure right now. In the next 10 or 20 years, that crown might pass to a new discovery. Perhaps an even larger, cooler, puffier supergiant buried deep in a star cluster halfway across the galaxy. It's not a sign of uncertainty or weakness in science that these records change. It's a sign of progress. Astronomy is not about locking down unchanging truths. It's about refining our picture of the cosmos as our tools and knowledge grow sharper. And when it comes to measuring the largest stars, every new crown bearer tells us something fresh about the lives and deaths of the universe's most massive suns. Measuring the distance to something as remote as UY Scuti isn't like pulling out a tape measure. It's more like trying to figure out how far away a lighthouse is by watching it from a moving boat, except the boat is Earth, the ocean is space, and the lighthouse might be surrounded by fog and changing brightness. The primary method astronomers use for nearby stars is parallax. This is the apparent shift in a star's position against the background of more distant stars as Earth moves around the Sun. Imagine holding your finger in front of your face and closing one eye, then switching to the other. Your finger seems to jump slightly. That jump is parallax, and it's incredibly useful because it's based on straightforward geometry. Here's the problem. For stars far away, the parallax angle becomes tiny. For UY Scuti, roughly 9,500 light-years away, the parallax shift is so small that it's measured in fractions of a milliarcsecond. That's a thousandth of an arcsecond, and 1 arcsecond is 1/3600th of a degree. In other words, you're trying to detect a movement smaller than the width of a human hair seen from kilometers away. Even with modern instruments, that's pushing the limits of precision. Historically, our ground-based measurements were plagued by atmospheric distortion. The ever-changing turbulence in Earth's air blurs starlight and makes pinpointing their exact position incredibly difficult. This is why early size estimates for many giant stars were way off. If we didn't know the precise distance, we couldn't accurately calculate their physical diameter. Space telescopes like Hipparcos and, later, Gaia have transformed this situation. Free from atmospheric distortion, they can measure parallax shifts down to microarcsecond precision. For many stars, this has completely rewritten our understanding of their distance, and therefore their size and brightness. But even Gaia has limits. At extreme distances, the parallax shift is so minuscule that even the smallest error bars can lead to big uncertainties. And then there's the issue of interstellar dust. Dust between us and the star can scatter and absorb some of its light, making it look dimmer and redder than it truly is. If we underestimate how much dust there is, we might think the star is farther away, and thus bigger, than it really is. Conversely, if we overestimate the dust effect, we could mistakenly shrink our size estimate. For UY Scuti, the uncertainty in its distance is one of the key reasons scientists say its size is about 1,700 solar diameters instead of stating it as a fixed number. If future Gaia data revises its distance even slightly, that could shrink, or inflate, its estimated size dramatically. This is also why Stephenson 2-18 might or might not be the true record holder. Its distance is still being fine-tuned, and with stars of this scale, a small percentage change in distance can translate to hundreds of solar diameters in radius difference. So, while parallax is one of the most elegant tools in astronomy, it becomes a razor's-edge measurement when dealing with far-off titans like UY Scuti. Until we develop even more sensitive space-based instruments, or perhaps even telescopes stationed far from Earth to create a vastly larger baseline for measurement, our crown for largest star will always come with a healthy dose of humility and uncertainty. When astronomers describe UY Scuti as a spectral type M4IA star, they're essentially giving it a detailed address in the grand catalogue of stellar classification, a code that tells us about its temperature, color, evolutionary stage, and even its luminosity. Let's break it down piece by piece. The M in M4IA refers to the star's position on the spectral classification system, which runs O, B, A, F, G, K, M. This sequence is ordered by temperature, with O-type stars being the hottest and bluest, and M-type stars being the coolest and reddest. M-type stars are at the lower temperature end of the spectrum, typically between about 2,400 degrees Celsius and 3,700 degrees Celsius at their surface. UY Scuti, with a surface temperature of around 3,300 degrees Celsius, sits comfortably in this category. This cooler temperature is why it emits that deep orange-red glow characteristic of red supergiants. Next, the 4 in M4 fine-tunes that temperature category even further. The numbers run from 0 to 9, with 0 being hotter and 9 cooler within the same spectral letter. So an M0 star would be on the warmer side of the M range, while M9 would be among the coolest. UY Scuti's M4 classification tells us it's right in the middle, cool for a star, but not the coolest possible in the M-class spectrum. The IA is where things get especially interesting. This is the luminosity class, which describes how bright the star is compared to others of similar temperature. The luminosity classes run from I to V, with I being supergiants, 3 being giants, and V being main sequence stars like our Sun. The addition of A in IA denotes an extremely luminous supergiant, the most luminous kind in the supergiant category. In fact, stars in the IA class are among the brightest in the entire galaxy, often shining hundreds of thousands to millions of times more brightly than the Sun. So when you put it all together, M4IA translates to a relatively cool star by stellar standards, red in color. With a mid-range M-class temperature, around 3,300 degrees Celsius. In the most luminous category of supergiants, IA, meaning it's burning through an immense amount of energy despite its cooler surface. Spectral classification isn't just about temperature and brightness, It's determined by analyzing a star's spectrum, the rainbow of light it emits when passed through a prism-like instrument. Within that rainbow, astronomers look for specific absorption lines, dark lines where certain elements absorb specific wavelengths of light. In UY Scuti spectrum, you'd find strong molecular bands from titanium oxide, which is a signature of M-type stars. These molecular bands form in cooler atmospheres where molecules can survive without being torn apart by extreme heat. The classification also hints at UY Scuti's life stage. M4IA stars are in the late stages of stellar evolution, having expanded massively after exhausting the hydrogen in their cores. The IA label confirms it's a true supergiant, not just a large giant star. It's a swollen, unstable star nearing the end of its life, and its spectrum tells astronomers that its outer layers are thin and diffuse compared to more compact stars. And there's another subtle point: this classification is not permanent. As UY Scuti continues to evolve, its spectral type may shift slightly. Its temperature could drop further as it expands, nudging it toward M5 or even later. If it begins to shed its outer layers more rapidly or contract before its final collapse, its luminosity class might also change in the years or centuries ahead. In short, M4IA is a compact code that says, this is a massive, cool, red supergiant at the absolute peak of luminosity, living in the twilight of its life. It's a label that packs a huge amount of astrophysical information into just 4 characters, a kind of cosmic shorthand for one of the universe's true leviathans. Studying a star like UY Scuti isn't just an exercise in gawking at cosmic extremes. It's a crucial piece of the puzzle for understanding how stars live, change, and die, especially the most massive ones. Most of our detailed knowledge about stellar evolution comes from studying stars similar to our Sun because they're plentiful, relatively stable, and easy to observe. But UY Scuti belongs to an entirely different category, the extreme end of the stellar mass and size spectrum. Its enormous radius, high luminosity, and unstable outer layers make it a living laboratory for phenomena we can't witness in smaller, calmer stars. One major reason it matters is because red supergiants represent a late stage of stellar evolution for massive stars. They've burned through the hydrogen in their cores, switched to fusing heavier elements like helium, and have swollen in size as the balance between gravity and internal pressure shifts. Understanding UY Scuti's current state helps astronomers test theories about how quickly such stars evolve, how much mass they lose in their final stages, and what conditions will trigger their ultimate collapse into a supernova. Mass loss is another critical area. UY Scuti's extended atmosphere and pulsations are constantly ejecting gas and dust into space. By measuring the rate and composition of this mass loss, scientists learn how massive stars contribute to the chemical enrichment of galaxies. Elements like carbon, oxygen, silicon, and iron, the building blocks for planets and life, are forged in the hearts of stars and spread into the cosmos when stars like UY Scuti shed their material or explode. Without massive stars enriching the interstellar medium, there would be no rocky planets, no water, and no life as we know it. Another reason UY Scuti is important is that it serves as a test case for stellar structure models. Our equations for how pressure, temperature, and density balance inside a star become more uncertain at these extreme scales. Red supergiants are notoriously difficult to model because their outer layers are so extended and turbulent. By comparing observational data, like pulsation patterns, brightness changes, and spectral features, with computer models, astronomers can refine their understanding of the physics governing such stars. There's also the supernova connection. Knowing exactly how big, massive, and unstable UY Scuti is today gives us clues about the kind of supernova it will produce and what kind of remnant will be left behind, whether that's a neutron star or a black hole. This helps improve predictions for other massive stars in our galaxy, including ones much closer to us, such as Betelgeuse. From a more practical standpoint, studying UY Scuti also pushes the limits of observational techniques. Measuring its size, brightness, and changes over time challenges our best instruments and methods. Every improvement we make in resolving such a distant, bloated object translates into better tools for studying other stars, exoplanets, and even galaxies. And then there's the philosophical side. Understanding UY Scuti's life cycle is part of a bigger human quest to know where we come from and where the universe is going. Every element heavier than helium in your body, calcium in your bones, iron in your blood, was once part of a star's nuclear furnace. When we study a star like UY Scuti, we're not just looking at an isolated object, we're watching the cosmic process that eventually makes planets and people possible. In short, UY Scuti matters because it's both an outlier and a representative, an extreme case that helps anchor our understanding of massive stars in general, and a cosmic participant in the grand cycle of matter, energy, and time. It's a reminder that even in the vastness of space, the life and death of a single star can ripple through the universe in ways that eventually shape entire worlds. Alright, let's put on our cosmic imagination helmets and actually try this. Imagine you're the pilot of a spaceship, not a warp-speed star destroyer or an interstellar hypercruiser, just a sturdy, reliable craft capable of cruising at the speed of a modern passenger jet on Earth. Let's say 900 kilometers per hour, about 560 miles per hour. We'll also assume you have infinite fuel, snacks that never go stale, and a very patient playlist, because you're going to need it. First, we need to know how far you'd be traveling. UY Scuti's estimated diameter is roughly 2.4 billion kilometers, about 1.5 billion miles. That's the diameter, so the circumference, the distance around its surface, would be calculated just like Earth's, using the formula. C equals /pi/times/text, diameter. Plugging in the numbers. C \approx 3.14 / times 2.4 text, billion kilometer. \approx 7.54 text, billion kilometer. So the distance you'd have to travel to make one lap around UY Scuti's surface, and I use that word loosely, since it's more like a wispy, turbulent outer layer than a solid ground, is roughly 7.54 billion kilometers. Now let's see how long that would take at our modest jet-like speed of 900 kilometers per hour. 7,540,000,000 text, div 900 text, approx 8,377,778 text hours. That's about 349,074 days, or 956 years. Yes, you read that right. At commercial airplane speeds, you and your spaceship would have to fly nearly a millennium just to make a single loop around UY Scuti. If you started this trip in the year 1069, you'd be landing around now in 2025, hopefully with your descendants still remembering what the mission was about. To put that in perspective, a flying around Earth at that speed takes less than 2 days. A flying around Jupiter would take you just over a month. A flying around UY Scuti takes almost 1,000 years. Of course, in reality, flying around UY Scuti wouldn't be a gentle sightseeing cruise. Its surface is a roiling, violent region of convective gas, with enormous updrafts that could span hundreds of millions of kilometers. These convection cells would make Earth's largest hurricanes look like tiny ripples in a puddle. The surface would be glowing red-orange and uneven, with massive star spots and eruptions of stellar material shooting out into space. Temperature-wise, you'd be in an oven-like environment, around 3,300 degrees Celsius, hot enough to melt and vaporize most materials instantly. You wouldn't be able to fly close to the star itself without your ship being incinerated in seconds, so our imaginary trip assumes some absurd SCIFI-level heat shielding or force field technology. And here's another kicker, because UY Scuti's outer layers are so diffuse, you could actually pass through them without encountering anything that feels like a solid surface. The density would be incredibly low, closer to a high vacuum than to Earth's atmosphere. But it would still be dangerous, because that thin plasma is moving at high speeds, emitting intense radiation, and would fry electronics, sensors, and your crew in no time without proper shielding. If you wanted to make your trip more manageable, you might think, well, I'll just go faster. But even at light speed, it would take you about 7 hours to circle the star once. We already covered that earlier. That means your casual subsonic airplane in space trip is essentially a time capsule project for future civilizations. So the thought experiment makes something very clear. UY Scuti isn't just big in the way a mountain is big compared to a hill. It's so far beyond human-scale thinking that our normal reference points collapse. The only way to truly grasp it is with absurd travel times, cosmic measurements, and a healthy dose of imagination. Let's shrink the cosmos down to something we can hold in our hands, literally. Imagine that Earth is the size of a small marble, about 1.5 centimeters across, roughly 0.6 inches. Now, in this scaled-down model, we're going to build a miniature version of UY Scuti so you can See, or more accurately, be stunned by, the difference in size. If Earth is a marble, the Sun would be a sphere about 1.6 meters, 5.2 feet, across, about the size of a big beach ball or a large yoga ball. That's already a massive jump. Our tiny marble Earth is suddenly dwarfed by this beach ball Sun. Now, replace that Sun with UY Scuti. Ready? In our marble Earth scale, UY Scuti would be a sphere over 2.7 kilometers, 1.7 miles, across. Think about that for a moment. You could take that little marble Earth, place it next to the UY Scuti ball, and you would need binoculars just to see the marble from the other side of UY Scuti. You could fit millions upon millions of marbles inside this enormous sphere, and you'd still have room left over. To give that some fun, grounded comparisons. Or if you put your marble Earth on one side of a city, UY Scuti would stretch from one end of the city to the other, and far beyond. In fact, if you placed it in the middle of Manhattan, its edges would extend well past the city, over into other states. Or if you were standing at one end of our scaled UY Scuti model, the other side would be over a 30-minute walk away, and you'd be walking in a perfectly straight line the whole time. Or in the same scale, an airplane flying around it would have to travel such a long curve that you wouldn't even notice you were turning until hours into the journey. And here's a fun mental twist. The actual Earth would fit into UY Scuti about 5 quadrillion times by volume. That's 5 quadrillion Earths. If each Earth were a marble, you'd need a planet-sized bag to carry them all. Even more striking is that in this scale, the space between the marble Earth and the yoga ball Sun is already over 160 meters, 525 feet. But for UY Scuti, that distance from center to edge would stretch beyond 1.3 kilometers, 0.8 miles. If you wanted to walk from its center to its surface in our model, you'd need comfortable shoes and a few water breaks. This kind of downscaling does something numbers alone can't. It makes you feel in your gut just how outrageous the size difference is. We humans like to think we're good at understanding big and small, but the universe operates in scales that laugh at our mental rulers. Compared to UY Scuti, Earth is not just small, it's essentially invisible, like a dust mote floating inside a cathedral the size of a mountain. There's something undeniably poetic about a red supergiant like UY Scuti. Even though it's a monster in terms of size, there's a kind of gentle, ancient beauty to it, a cosmic ember glowing in the dark. Its reddish hue isn't just an artistic flourish from astronomers' images. It's a direct consequence of the physics happening inside the star. The red in red supergiant comes from its surface temperature, which is much cooler than that of smaller, bluer stars like our Sun. UY Scuti's outer layers hover around 3,300 degrees Celsius 5,972 degrees Fahrenheit, compared to the Sun's -500 degrees C, 9,932 degrees Fahrenheit. That difference in temperature means the peak wavelength of light it emits shifts toward the red end of the spectrum, giving it that deep, warm, fiery glow. And it's not just a flat red, either. Through a telescope, the surface of a star like UY Scuti would appear mottled, textured, and alive with motion. You'd see huge convection cells, each hundreds of millions of kilometers wide, slowly boiling on its surface. Some regions would appear darker, cooler star spots, while others would be brighter, almost golden orange. These variations happen because the outer envelope of a red supergiant is so bloated and diffused that energy moves around in massive updrafts, rather than the more evenly distributed surface we see on the Sun. From a distance in space, UY Scuti would be a dazzling point of light with a subtle reddish tint, but if you could somehow approach close enough to see its full disk without being vaporized, the view would be overwhelming. The surface wouldn't be smooth, it would look like a chaotic, boiling ocean of glowing plasma, with swirls and eruptions sending arcs of gas out into the surrounding space. The color also plays tricks with our perception. In human culture, red often symbolizes warmth, passion, and even danger. And in a sense, UY Scuti embodies all of these. Its warmth is beyond imagination, it's a fiery and unstable presence, and it's nearing the end of its life in a final, spectacular burst. It's also worth noting that many of the most visually striking stars in our night sky, like Betelgeuse, share this reddish color, which makes them stand out against the cooler whites and blues of other stars. Why does the red look so soft compared to the intense blue-white glare of hotter stars? That's because cooler stars emit more light in the red and infrared range, which is less blinding to our eyes than the higher energy blue light. If UY Scuti were visible in our sky, It wouldn't have the harsh, eye-searing brightness of Sirius. It would be a giant, gentle beacon, glowing like a hearth in the darkness, yet covering a huge portion of the heavens. But there's also something bittersweet about that glow. It's a sign of a star that has used up much of its core fuel. The reddish light of UY Scuti is like the dimming embers of a once blazing fire. Beautiful, yes, but also a herald of change, marking the transition from a long, stable life to the final, explosive finale of a supernova. Despite being one of the most talked about stars in astronomy circles, UY Scuti remains an enigma in many ways. We've measured it, photographed it, analyzed its light, and even given it a spot in the largest star record books. Yet there's still a great deal we don't know, and in some cases, we can only make educated guesses. One of the biggest unknowns is its exact size. You might think that with today's advanced telescopes and measuring techniques, we could nail down something as straightforward as how big is it. But the truth is far messier. Because UY Scuti's outer layers are so diffuse, they don't have a clear, sharp edge the way a solid planet does. Instead, its atmosphere gradually thins out into space. Deciding where that surface begins is tricky, and different measuring techniques can yield slightly different results. Add in the fact that UY Scuti is nearly 9,500 light-years away, and tiny errors in distance measurements can balloon into huge differences in estimated diameter. Then there's its variability. UY Scuti isn't a static star. It pulsates, expanding and contracting in cycles that change its brightness and even its apparent size. If you measure it at the peak of expansion, you'll get one size. Measure it at a contracted phase, and you might shave off hundreds of solar radii. This variability makes it challenging to pin down a true value for its size, which is why astronomers often give a range rather than a single figure. We also don't know the full details of its internal structure. While models of stellar physics give us a good idea of what's happening, fusion in the core, layers of different elements surrounding it, convection in the outer layers, we can't directly see inside. Much of our understanding comes from studying similar stars and running computer simulations. But every star is unique, and UY Scuti may have surprises lurking within. For instance, we don't know exactly how much mass it has shed into space during its lifetime, or precisely how fast it's losing material now. Another uncertainty is its exact timeline towards supernova. We know it's in its final evolutionary stage, but whether it explodes in 100,000 years or just under a million is still anyone's guess. Stellar lifespans at this phase can be difficult to predict because they depend on complex processes happening deep inside the star that we can't directly observe. And perhaps the most fascinating unknown: what will be left behind? Based on its estimated mass, UY Scuti could leave a neutron star. Or, if its core is massive enough after the explosion, it could collapse into a black hole. We can only speculate until we actually witness its end, which, frustratingly for impatient astronomers, probably won't happen for many, many human lifetimes. There's also the larger mystery of whether stars like UY Scuti even represent the true upper limit of stellar size, or if there are still bigger, more extreme stars hiding in our galaxy or beyond. Our instruments are improving every year, and with tools like the James Webb Space Telescope and future interferometers, we may one day measure UY Scuti more precisely, or discover something that dwarfs it entirely. For now, UY Scuti stands as both a milestone in astronomical discovery and a reminder of how much we still have to learn. It's a cosmic riddle wrapped in plasma and light, visible across thousands of light-years, yet holding on to secrets that may take generations of observation to unravel. When we stand under a clear night sky, even without a telescope, we are already looking into infinity. Yet knowing that somewhere out there, hidden deep in the constellation Scutum, is a star like UY Scuti changes the way that sky feels. Suddenly, those points of light aren't just dots. They are worlds, furnaces, and in rare cases, titanic beacons whose scale dwarfs the very framework of our minds. UY Scuti is not simply large in the way we normally use the word. It's not just bigger than a mountain, or bigger than a planet, or even bigger than the orbits of planets. It is beyond our intuitive grasp of size. You can throw every analogy at it: marbles versus stadiums, grains of sand versus skyscrapers, and still, the truth will slip between your fingers like stardust. Its bulk is measured in light hours, not miles or kilometers. Its girth could swallow our solar system whole. And yet, it's but one star among hundreds of billions in our galaxy alone. This is where UY Scuti becomes more than an astronomical curiosity. It becomes a mirror for our perspective. When we measure it, compare it, and marvel at it, we're not just learning about the star itself, we're confronting the edges of our imagination. It forces us to admit that our brains, honed over millennia to judge the distance of a thrown spear or the depth of a river, are not naturally equipped to comprehend cosmic enormity. And still, we try. That act, the stretching of our mental boundaries, is perhaps one of the most human things we can do. In UY Scuti, we see not only grandeur but impermanence. This colossal star, with its gentle red glow, is in its twilight. It will not live forever. In cosmic time, it's already packing its bags for its final performance, a supernova that will light up its corner of the Milky Way and leave behind the compressed core of what was once the largest known star. Even giants fall, and in their fall, they create the raw materials for new worlds, new suns, and perhaps new life. And so, UY Scuti reminds us of two truths. First, that the universe is staggeringly, humblingly vast. Second, that it is alive with change. Nothing stays the same, not even the titans of the cosmos. Its immensity challenges us to think bigger. Its fate teaches us that even the most powerful have their limits. The next time you look up at the stars, remember that beyond the familiar constellations are wonders like UY Scuti, wonders so vast that if you could somehow stand on their surface and survive, your horizon would curve away into red fire, and your concept of sky would never be the same. We may never touch it, we may never witness its final blaze, but simply knowing it's out there stretches the borders of human thought into places they've never been before. UY Scuti doesn't just live in the depths of space, it lives in the depths of our imagination, a glowing reminder that the universe is far stranger, far larger, and far more beautiful than we have yet begun to dream. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.